My name is Sota Ueno. The title of my talk today is Distributed Persistent Signals Architecture and Implementation. Today, IoT is becoming more popular. Many IoT services are introduced by connecting sensors and devices with communication infrastructures and data in the cloud. There are three characteristics in IoT systems. The first one is linkage of data flows. An update or value is propagated through the IoT networks. The second one is handling of time series data. Time series data is often used in IoT systems because IoT devices such as sensor and thermometer always handle time varying values. The final one is distributed systems. An IoT systems consists of many devices and services connected over the network. Sometimes such a system is organized by connecting independent systems. For example, we can create a new service by connecting existing ones. We consider that reactive programming is promising to develop such IoT systems. Reactive programming is a programming paradigm that fits for writing programs that handle time varying values such as inputs from user and the environment. It allows programmers to declaratively specify the data flows. In the reactive programming language SignalJ, we can declare such a time varying values using the modifier signal. Here is a data flow from A to B. We can imperatively update the source of the data flow. So we can perform an incrementation on A. This update is automatically propagated to B. So B is initialized by 10. But after the incrementation, its value becomes 12. This mechanism is used for the linkage of data flows. SignalJ can preserve update history persistently. This feature is useful for handling of time series data. For example, here is a vehicle class for a vehicle tracking system. By the modifier persistent, the signal X and Y are internally connected with a time series database. Other signals such as dx, dy, and v that depend on x and y are also connected with the corresponding database views. The corresponding database table and views are identified by the parameter ID. So, instance, the VE on the right-hand side represents time series data identified by the ID orbiter 1, 2, 3, 4. The problem is that Signal does not support it. The problem is that SignalJ does not support distribution of persistent signals because the binding to the database is specified by a configuration file. Our contributions are to propose an architecture for making SignalJ distributed and to provide solutions for several challenges to realize such an architecture. We identified the following challenges to realize distributed persistent signals. The first one is location transparency. The second one is making use existing time series data. For example, exist many legacy time series databases, and it is necessary to represent them as persistent signals. The final one is synchronization of time series data. We need to consider the network latency of update propagation and the glitch avoidance. Location transparency is necessary because SignalJ realizes time series data at high abstraction level. So location of the corresponding database should be invisible from the programmer. We also need to consider several data sources distributed over the network. The next challenge is the use of existing time series data. Actually, legacy time series data always exists at the source of the data flows. So it is necessary to introduce a mechanism to initiate the update propagation on such legacy data. There are also subtle problems. The legacy data format is not standardized, and there are several kinds of data sources, such as Excel, relational database, and so on. In this talk, we assume that time series data is represented using a signal table, and each table has a column for timestamp. With such assumption, it is easy to convert existing time series data into a relational database table. Synchronization of time series data is important because inconsistency can occur during update propagation because of network latency. For example, in the right diagram, CC refers to AA. The propagation of updating AA to 555 can delay and supersede the propagation of update AA to 333. So, when calculating the values of signals over the network, we can't rely on the arrival order of update propagation. We also need to consider join of data flows. In this code, the persistent signal CC depends both on AA and BB. We need to judge whether the update of AA and BB are synchronized. I mean, AA and BB might depend on the same single source, or these two are independent. But the programmer knows that they are updated almost the same timing. To tackle these problems, we propose the following solutions. The first one is ID resolution. The next one is update propagation using database triggers. The final one is synchronization using timestamps. Here is an overview of our architecture. Our architecture consists of an ID resolver, signal class instance, and their corresponding database. In this diagram, all signal class instance A, B, and C execute on the same memory space, but the database can be distributed. The connection between signal class instance and the corresponding database is created when the instance is created. The ID resolver tells the location of the database when this connection is made. ID resolver consists of a key value table that stores pairs of ID and the information that is necessary to access its corresponding database, such as its URL, password, and username. This ID resolver is accessed when the constructor of signal class instance is executed. Using the information provided by the ID resolver, the signal class instance creates the connection with the database. Update propagation is implemented using database triggers. This means that each table is equipped with a trigger that notifies its update. The right diagram shows the process of each signal class instance during the update propagation. First, the instance receives an incoming request from the upstream signal to update its value. Then, this instance issues an update query to the database. The database asynchronously notifies the instance that the update is completed. If this database is migrated from the legacy timeseries data, this notification initiates the update propagation. Finally, the signal class instance propagates its update to the downstream signals. Synchronization of update propagation is managed using timestamps. An update is propagated with its timestamp that is initially assigned by the database. This timestamp is used to keep consistency of timeseries data throughout the data flow. If the persistent signal is a join of multiple persistent signals, there are several policies to select the timestamps. One example is multi-source bufferless synchronized policy. In this policy, the update is postponed until when all the incoming updates are received. For example, this persistent signal C is a join of A.AA and B.BB. In this diagram, the value of C is updated when the update of B.BB is received. The value is calculated using the latest value. So, it inserts the value 7 with timestamp T3 into the C's corresponding database table. We also classified other policies. They are detailed in the paper. Now, I summarize the properties of our architecture. It supports reactive programming in the open and distributed setting. We consider that our system makes it easy to use data flows developed by a third party, including the legacy ones, to construct another data flow over them. This is because the data source is identified by its ID and connecting using a high-level abstraction representing data flows. Another property is its single source glitch avoidance. In the left code, the persistent signal CC depends both on A.AA and B.BB, and B.BB also depends on A.AA. This will cause an inconsistent situation if CC is updated before B.BB is updated. Using the proposed update policy such as single source bufferless synchronize, it ensures that CC is updated only after both A.AA and B.BB are updated. All their updates share the same timestamp, so glitch can be avoided in our architecture. I briefly explain how this proposal is implemented. Our implementation consists of time-series database and SignalJ runtime library. A time-series database is used to keep update history of persistent signals, and it is equipped with triggers that notify their updates. The SignalJ runtime implements The SignalJ runtime library implements the behavior of signals, including persistent ones. For time-series database, we use timescale.db, an extension of PostgreSQL. A signal class instance is implemented using corresponding database relation with the current timestamp. Each relation is equipped with a trigger. Here is a template of that trigger. This is implemented using the create trigger statement, supported by PostgreSQL. Each signal class instance is specified by the table name parameter for the template. The asynchronous notification is implemented using the PZ notify event, which is also supported by PostgreSQL. A SignalJ program is compiled into a Java program that uses SignalJ runtime library. This library implements the behavior of signals. For persistent signals, it provides connection with the time-series database. It accesses ID resolver to obtain the database access information that corresponded to its ID. It also listens the PZ notify event from the database and performs update propagation to the downstream persistent signals. As a proof of concept, we implemented a simple sample application based on our proposal. This is fan controller that uses the legacy time-series data that monitor temperature and humidity. commutative. Migration of these time series data into persistent signal can be performed mechanically. Using them, we introduced a persistent signal DI that represents the discomfort index. Based on this discomfort index, the fan is switched on and off. And now, I would like to discuss some related work. There is much work on distributed reactive programming and many proposals to perform distributed update propagation. But persistency is not considered. Persistent signal is related fault-tolerant reactive programming that provides the snapshotting mechanism for signals. Our approach is more focused on application that query over time series data. Event correlation mechanism is related to our synchronization policies. Here, our proposal focus on focused on variations of the zip operator. I would like to summarize my talk. I have proposed the architecture of distributed persistent signals, identified challenges to realize that, and proposed solutions to them, such as ID resolution, update propagation using the database trigger, and synchronization using timestamps. For the future work, we need to perform more case studies targeting to larger systems. I also consider that ID management mechanism is necessary to avoid name collision. This is the end of my talk. Thank you very much.
Thank you very much. So, questions, comments?
Thank you for this presentation. I was wondering about you said something about you used an extension of PostgreSQL. We'll call time scale or something. What did this extension give you? What did this extension provide? So this was a couple slides earlier. You were talking about database. Which database you were using?
Which database use?
Yeah, timescale DB. I've not heard of this before. Why did you choose this extension?
Yes, question. So timescale DB supports some suppose the time-oriented queries that have so timescale DB supports some time-oriented queries such as using the special index for the timestamp. So for example, to select some rows within the some specified time duration or something like that. And it also supports some performance aggregation based on the timestamp. So we use this database.
Okay, thank you.
Okay.
In the middle of your presentation, you mentioned that the databases are distributed, but that the system itself isn't distributed. Are there any plans or ideas out there to also distribute these objects across different machines as well?
Are you right? Pretty sure. This one, sorry. Pretty sure the architecture of yeah,
That's the one I was
Yeah.
referring to.
So, well, we, yeah, we consider that we can also the same architecture can be, applied for the in the case of the object is distributed, but we haven't worked on this setting yet. Thank you.
Okay, any other question, comment? No comment from remote side? Okay, I have one question, maybe a simple question. Yeah, persistent signal is very, interesting idea. So I think you can go back to in the past. And it's let's say, so different from the ordinary reactive programming. So do you have any idea for, so let's say, utilizing such features or from the past? Especially for the distributed data.
Yes, I'm looking for the yes, interesting applications. Yes, we currently we just have API that so we can go back to some anytime and to what can I say reproduce the station at that time, but yes, but IoT application always use the many kinds of time series data. So we might we might consider some interesting application using our setting, but we are still working on this direction. So.
Thank you very much. So any other question, comment? Okay, so thank you very much. Thank you.